Good morning, everybody. Congratulations on making it in. You are the winners. And now you can look in shame at the folks who come in late. So congratulations for that. We've got a great session for you this morning on uncertainty and exploration. It's kind of my favorite thing. So to start us off, I'm going to introduce Claire Vernade, who's going to talk to us about memory traces.
All right, so yes, welcome everyone for this morning session. Thanks for making it early. So this talk is a bit going to be about a really new work that I did with Onno Eberhard, my PhD student, co-supervised with Michael Mühlbach from the Max Planck Institute for Intelligent Systems in Tübingen. Before I start, I would like to thank Jan, who I'm not sure if she's in the room. She's over there. Yes, we spent an hour together preparing this talk. This was a super good idea by the organizers of this conference to, put like dry speakers like me with wet advisors so that we can like find a good way of presenting these results in a way that's like accessible to everyone and really like I hope the talk is up to like all the amazing comments that you gave. All right, so today we're going to talk about memory, which is a key problem in decision making. So we're going to talk about this once the clicker wants to actually click. Maybe it's just clicking on it. Okay, perfect. Yes, it does. Perfect. All right. So almost any card game that you can think of, like the hard ones, like the bridge, or for the French in the room, the tarot and the belote, and all these like long sequential games are actually not something that you can play reactively, just looking at your card deck right now, like at your hand, and then making the optimal decision. You need to remember the sequence of things that happened on the table for the past interactions, and even sometimes for the past games, right? The past several games. Like in tarot, for instance, we never reshuffle the deck, so like you really have to remember all the things that happened before if you really want to play optimally. And so we see that like in a lot of these sequential games like this, it's very important. Like you have partial observability. You only see your deck right now. You don't know what happened in the hands of the others. And you need to use your memory to make the decisions. And this is something that somehow, the classic reinforcement learning setting, like the classic MDP doesn't represent well. And so we have to do things a bit differently. So a typical model of the problem that I just described could be the following. At time t, I'm in a state st, which is something I do not observe, and I observe instead the observation, some very simple observation, typically my card deck. And according to this observation, I should be able to take an action that this action will affect the actual state of the game in a way that actually I'm not able to understand. And so this, making this action from this observation is actually rarely a good idea, as we discussed before. And instead, what you want to do is build, kind of memory models, something that you can keep in your mind and that will help you make the actions instead, and that will be more useful than just the simple observation right now. So we're gonna talk about this problem quite a bit. So let me introduce it. It's a simpler problem than bridge or all these card games, and it will allow us to make more formal statements down the line. So typically, this is a very simple deterministic corridor game where you enter from the left here, and when you enter, you see a light, you see a signal. The signal is either red or green. And then it's a deterministic environment. You're going to walk through this corridor. I'm walking backwards. So you're going to walk through this corridor until you reach this blue place here. And in this blue place, you have to make a decision going left or going right. This is the only real decision you have to make in this game. If you go left, and you were in the red environment, then you get 1 reward. And if you were in a green environment, you don't get the reward, or you get a negative reward. So at the blue place, you need to remember what was the observation from the beginning, right? Because right now, in the blue place, you actually don't see the color of the world anymore, right? So the only way for you to make this good decision at that place is to have a way to remember what you saw in the past. So somehow what we want to do, in this very simple, partially observable setting, we want to be able to construct this memory that is up there, something very simple, that doesn't take too much space and that actually has the information that you need to make the right decision. For those that arrive right now, it's perfect. We just introduced the actual problem of the talk. So please find a seat. Awesome. Okay. So concretely, what is going to be, going on in this talk is that we're going to see histories of observations, that I'm often going to denote H. And H is always a sequence of observations like this, these Ys from this Y space of observations. And these observations are one-hot encoded. So they are these very simple vectors where you have like a few slots and only one is 1 or 0 to indicate what is the current observation. And the problem is that there are, so if you are leaning on this wall over there, can you please sit in the room so that we do not have these issues with the light that we had yesterday? Thank you so much. All right. Okay, so the problem is that there are, given a certain number, given the length of this corridor and the size of your world, there are an exponential number of different histories, right? This set here, it's a set of a certain of k vectors that are one-hot encoded, and in principle, it's a big combinatorial. There's a big combinatorial number of them. There's actually y to a k number of possible histories, right? So you need to find a way to compress or represent these histories. So the first part of the talk is going to be about that. The second part of the talk, we are going to use these histories and this compression algorithm, the blue part of the talk. We're going to use it to do a policy evaluation task, right? So we are going to ask the following question: if I observe an agent, can I evaluate its value function? Where the value function is now going to be a function of the whole histories, right? Not just the state, because the state, we don't know it, right? It's going to be a function of the history. And we're going to ask whether, some representations are better than others to do this task. Okay. So this is an old problem in reinforcement learning and decision making where, there are lots of people, probably including in this room, who have worked on this. And just, typically what people would do in practice in this kind of settings is they would kind of plug an RNN or an LSTM in the middle of this loop that kind of learns this representation and helps the agent make the action. There are other types of models like neural Turing machines or utile distinction memory, like these kind of things that use trees to represent the memory. But in this talk, we're going to be a lot more theory focused. Really, the goal is going to be to look at these function spaces that we get from these different memory compressions and try to see if we can compare a very basic strategy, the frame stacking or the memory, the simple window strategy of remembering only a finite set of observations with something else that we're going to introduce that is called the memory trace. So what are memory traces? Memory traces are vectors that are in the same dimension as the observation space, and that are going to be kind of updated in just a moving average kind of style. So they look like elicitation traces, but reverse. Essentially, what they do is, can I actually do this? Oh, well, okay. So at time t, when you see an observation yt, the current vector, this one or this one, what you do is you multiply it by 1 minus lambda, and you add it to the previous one that you discount by lambda. So it's super easy, right? It's very efficient update. And you get a vector that's kind of compressed like this. And what it gives you is something like this. If you see red at the beginning, you have 1 minus lambda, and then this red thing is going to be multiplied by lambda the whole way through, and so you have this coefficient here, right? And then the same thing for the other coefficients. So you have these other coefficients that computed for you. But for the green one, right, you have this coefficient on the first coordinate. So what happens is these two vectors, as lambda goes, as the power here goes really large, the two first coefficients, they're going to go to 0. But, one is going to be non-zero and the other one is going to actually be 0. I'm going to say again the same thing. The people that are standing over there along the wall, to avoid any blinking of the lights, can you please find a seat in the room, just so that we don't, yeah. Cool. Yeah. Can you not lean on this wall, please, and sit somewhere? Yeah, awesome. Awesome. Okay. So yeah, so we have memory vectors like that look like this, like in the dimension of the observation space. And the question is going to be, are they good enough to help me make the decisions that I need to take? Are they going to be separate enough so that my agent can use them to make actions efficiently? Cool. So let's look a little bit at what these vectors look like. What is this space? Haha. Okay, so what's going on? Okay. Thank you. Seems like there's no way to avoid this. All right. So, okay. So what is this space of function looking like? So we are going to just remove the first coordinate because in this example, it's always white, so it doesn't play any role. And the way it looks like is that at the beginning, when I only have one element in my history, essentially I have 3 types of vectors in my memory trace space. I only have A, B, or C, depending on the observation. Then when I have 2 vectors, like 2, I'm going to add them up, with this discounting kind of effect. And so they start looking like this. And then 3 vectors, I'm adding them to this map. So like, this is exactly, I'm representing exactly these vectors. They are in dimension 3, but I project them on the 2D space. And so we start seeing that, like, the one that have like more A's, like early A's, they are here. The old, the old observation starts being discounted. Okay. And then long term, sorry, it's a bit pixelized, but you'll see why. So long term, you have like when you have 8 elements in your history, you start having this kind of like very dense like sets of points that start making this kind of fractal structure, where the top point here is going to be the history that was just A, like red, right? Whereas the one next to it had like a B at the beginning, but it's not very far from the original one. So like, these points are going to get closer and closer. And what we don't want in principle, I mean, intuitively, we don't want them to overlap. Because if they overlap, then I have 2 vectors that are the same place, but that don't represent the same history. So they could make us make the wrong decision in principle. But what we're going to see is that like the story is a little bit more nuanced than that. So concretely, we're going to try to discuss if you should, what happens when you try to memorize the past fast or slow. And that actually depends on your choice of lambda here, the forgetting coefficient. So this is, okay, I don't know if I can. So, okay, here I'm making lambda very short and then very, very big, right? And what happens when lambda, the memory gets long, when lambda gets close to 1, the memory gets long, these points start kind of mixing each other. So like they're no longer separated. So before, maybe I can replay it. Yeah. For small lambdas, this point, they get closer and closer, but actually we can prove that they never overlap. So the histories are always separated. Whereas for kind of longer memories, they will overlap. So how do we deal with this? Like, is there a way we can say something about like, is it good or is it bad? And in what kind of situations? Okay, so this was just the part 1. We introduced memory traces, and now we know a few things about them. First of all, they're super efficient to compute, right? It's like it's just a no-brainer. Like you just add the things with like some like geometrical discounting, and they have a nice separation property for like small, for small memory, for short memories, but not for long memories. Okay, and what we don't know yet is what's the, like what's their power to represent functions. Okay, perfect. So in the second part of the talk, like I said, we're going to try to use these Z's, right? These memory traces to evaluate the policy of an agent. So the value function is exactly the one you are used to. It's the sum of the discounted rewards, but the state is not a state. It's an infinite set of observation until now. The place where I'm now. So it's a very complex combinatorial object in principle. And I'm going to try to do function approximation. So I want to try to find a function that takes as input a memory trace or some other compression of the history, right, instead of the full combinatorial object, and tries to approximate this well in the sense of minimizing the least squared error. So the risk here, that is the sum of squares, the expected squared error. Okay. So in practice, often what people do is to just have like a lot of histories, right? You generate many trajectories, and then you try to minimize this squared error empirically. That's classic machine learning stuff. So the set of functions we are going to look at are these two different type of compression or representation: the window, the trace, and the window, the frame stacking strategy, and the memory trace. So the window that I haven't really properly defined so far is simply like the set of functions that are written exactly like this. Like it's any function that is written as the composition of, a function, some function, and a window of size m. So meaning the exact set of like the past m observations. So you keep this like m times d kind of box of observations, and you pass them to any function. So this is kind of a function on a big discrete set. And it's, it has a large memory cost, but that is easy to know what it is. It's like somehow something like y to the m, right? And on the other side, you have like the Lipschitz functions with that take as input the trace. So here I'm going to first compress the history with the trace, the memory trace, and I'm going to apply some function that is Lipschitz. So it's like smooth enough. There exists a constant L that controls the variation of this function. This constant could be large, but we're going to discuss this. So to compare these two sets of functions, we need a way like to measure. We need a quantifier. So we're going to talk about metric entropy, and I know that it's not something that not everybody may be familiar with. So I'm gonna try to give you an intuition of what this is. So the metric entropy of a function class is measures how many functions are needed to describe the whole class up to a small approximation. So we're gonna give ourselves an epsilon, right? And we're going to look at how many different objects, like how many different objects do I need to describe my function? So typically in a discrete setting, which is, relevant to our problem, we would have something like this. It's a bookshelf. And on my bookshelf, I have like many different books with different colors. What do you think is the metric entropy of this set, of this function class? I know it's 920. So if you wanted to describe this bookshelf to someone, you would say there are books and they are either green, blue, or red. So there are essentially three, NE, right? The covering number is 3. There are 3 functions that describe these books. Up to small variation, this variation is the kind of the new, how is it called, like the nuance, right? Like the clarity of the color, right? So the metric entropy is going to be the log of 3. Easy. And in more classic functions that we know, like the ones that are Lipschitz typically. So this is a Lipschitz. This is a class of Lipschitz function, plenty of like wiggly things. Like here, you see like the wiggly things. You could describe them as like it's essentially either a line like this or a wiggly sinusoid plus linear function. So like the metric entropy is essentially going to be a metric of like how complex how many elements do you need to describe the set of functions that are there. And as you can see, like the more functions you need, the more complex is the function space. Like if I had put like 10 colors here, would have been like very difficult to describe it, right? You would have needed more basis function, if you will. Like it's a bit of the notion of basis function, but within some sort of distance. Okay, so we're going to look at the metric entropy of our two function class. The function class that uses windows and the function class that uses Lipschitz function of the memory traces. So the first result that we have is that when you are forgetting fast, when you set your lambda smaller than 1/2, essentially what you're doing is somewhat equivalent to memorizing a similar amount of information. Or more precisely, the theorem that we prove is that for every window of size m and some forgetting factor lambda, like smaller than 1/2, there exists a Lipschitz constant that can be really, really high. So it can be very wiggly functions or very smooth functions. There exists a Lipschitz constant such that the risk of, my memory trace is bounded by the risk here. And essentially, we also prove that they have similar complexity, similar metric entropy. So the way you can visualize this proof, it's a bit longer than that, but the way you can visualize this proof is that essentially, if you have a discrete space like this and a discrete function, the red points are the functions that my, the window are assigning to these discrete objects. Like you can fit a smooth function across these points that uses some memory trace, right, and some Lipschitz constant. Like there is a sort of way to like fit the function with like a small lambda, and this is due to this kind of separation property that we saw earlier. On the other hand, if you have slow forgetting, if your lambda is long, if your lambda is larger than 1/2, then we prove that like memory traces with long memories can represent some histories that are more simple, like that more simply kind of or simply what that are more simply described than windows. So let me give you an example. Typically in this T maze that we saw at the beginning, we know that the only way that the learner can do something smart here is to remember this thing. So the only window that is useful for this problem is the window of size k. It's like keeping in memory the whole length of the corridor. So we know that like the function class essentially that needs to be, that is useful for this problem has a complexity of the order of y to the k, right? It's exponential in the size of the environment. And on the other hand, we prove that if you set the memory trace parameters to k-1 to k, so something very close to 1, and a small Lipschitz constant, so you actually have something that's linear in k, so like a reasonably smooth class of function, you can actually separate the histories. So this is not trivial, like it's not obvious from this example, like, but this is essentially like the key results, of this paper. One of the key results of this paper is that there are ways to represent complex, like long-term memory issues, like this long-term memory problems with memory traces, such that the metric entropy, the complexity of the function class that you use to approximate your problem is actually polynomial in k instead of at least exponential in k for memory for window types of memories. So maybe to show a little bit like some kind of extra exploration that we did in this space. So far, we've only talked about value function estimation, right? But like if you wanted to learn with memory traces, what you would do is essentially you would replace the current state with the memory trace. right? So you take some lambda and you start stacking the observations into a vector. And here we actually took two lambdas. We took lambda equals 0, or essentially like just keeping the current observation. And we stacked this memory trace, this very simple, trivial memory trace with like the smart memory trace that is given by the theory, right? It's the one that assigns lambda to like the right very long memory value on this T maze thing. And then we let K vary. And we look at how the agent performs as a function of K, and as a function of like, with different types of memory, memory representation. So we compare the memory trace with like the stacking of the 0 plus the lambda K, the memory trace with just the lambda K, so we don't actually see the current observation, and the window of size K. Right, and we also compare the memoryless, so the one that is just reactive, that just takes the action as a function of the current observation, which doesn't do good. So essentially it does random because it's plus or minus, like the reward here is, so it does a random decision at every step. So not so good. But so what we see is that, memory traces in long corridor situations, memory traces give us like an extra boost to our PPO. This is not so, like our results don't explicitly explain this, right? All it says is that there is a simpler way, like there are simpler functions that would represent the value, value function of this agent. So perhaps what is happening is that PPO is simply, fitting an easier function in a way, like finding a better minimum thanks to the representation. But it's like, this is speculative, right? We don't have an explicit proof for what is going on here, but like, it's interesting to see that like this kind of complexity analysis actually resonates with empirical results of this kind. Cool. So yeah, conclusions. I think I'm not sure I need to convince everyone here that that partial observability is actually crucial and central in decision making. I think it's a fairly well shared point of view, but the problem is that it's really hard to handle with reinforcement learning. It's not impossible, right? Like there are lots of work on this, but I think the question of representing memory in ways that we can formally understand is still kind of open, or at least there are lots of open questions in this space. And yeah, I think in this paper we make this one first step in proposing a very simple, computationally efficient way of representing the memory. And we show that it actually, approximates the value function really well, and that it could serve the purpose of training better agents in reinforcement learning. Thank you for your attention.
Thank you for that talk. I can hear, but the thing is, I'm a computational neuroscientist. I'm wondering that since yesterday I just said that number that we kind of memorize our, let's say, child differently based on how important or how impressive the memory is. For example, in the teammates also, I would believe the first grade are more important than the other grade in the corridor. How you think about this, or how you might reflect that in memory trace?
Yeah, that's a very good question. So I don't know if I should repeat the question. So the question is that like we have, like I guess paraphrasing, like humans seem to have a good capacity at understanding what is important to remember and what is not, and then like kind of building a memory in a way that like kind of keeps track of the relevance or the information kind of gain from some of the previous observations. Here, yeah, it's true that it's completely agnostic and that our lambda is not y dependent, right? The lambda that I use at a certain time t to update the trace doesn't depend on what is like the quality of y. This is actually I think it's a very tricky question, like mathematically to to kind of, if you start saying that I would like a lambda that is dependent on what, some sort of information quantity that depends on like with this observation, I think it makes the mathematical analysis difficult. But I agree with you that it would be, it would be a better way of compressing, of compressing the memory. If you want to really compress, and I think this is perhaps like, a good area, a good direction to actually study compression in a way that like takes into account the validity of the signal. Another thing you could, yeah, I don't know. I'm not sure I have a lot more comments because this goes way beyond like our analysis, but this is a very good point. There's a question here.
Hi, yeah, nice talk. As I think you know, right, there's a big interest in the language sequence modeling literature, like the transformer literature on alternatives to transformers that don't need to keep all the past into and do quadratic attention. So the whole state space modeling line of work falls into a camp that's very similar to what you described. And like the Mamba line of work in particular builds a set of basis functions that takes weighted combinations of the past and has some sort of provable properties. I wonder if you can talk about the connections.
Yeah, so yes, so state space models are very close to what we're doing. They're also this kind of, yeah, I don't know, where is my last memory trace, but they also have this update kind of style that's like kind of taking the previous state and updating it with like some linear function. So it's like a linear filter of the past. And we are looking into like linear filters, like equivalence, like of, this with like linear filters and trying to see if we can generalize to more linear filters. So like for now, we essentially have a filter that does something like this. The filter kind of exponentially decreases the past memory, but we could imagine other types of filters, that like take different, that have different geometries that like also could like take more of the past, or have like more of a kind of window style, like something that interpolates a bit more between the different types of memories. This is really ongoing work. I think Ono, my student who is over there, might have more answers about this, and he will be at his poster, like at our poster tonight. Sadly, actually, I have to leave shortly after my talk, so I will actually have to defer the further discussions to Ono. But like, we are working on this, and yeah, some weird things happen that like somehow if you combine the linear, like other linear filters with the memory traces, we're not really managing to put our fingers on what else we can do that's that's more powerful than this. But like, I think it's yeah, I will defer the discussion to Onu.
Thank you, Claire, for really great talk. To come back on the previous question, I wanted to understand what is the advantage of using your memory traces in comparison to using an RNN or a transformer, for example, because I have the feeling that like if we take RNN, they are going to learn what is important to remember and what is important to forget, actually. And so what is the typical scenario where using memory traces actually has a crucial advantage over those existing methods?
I don't think there is such thing. So really, like like these advanced networks for like sequences, the RNN architecture, the LSTM transformer state space models that have been carefully designed to, remember the right set of information and things. Like in practice, I would definitely do this. What the problem is that like in print, we can't say much in theory about them. We actually don't know, how they differ, like why one would work better than the other. Typically, it's a very common thing to do like some frame stacking to like remember a certain subset of like your past frames, maybe like send it through, some RNN, and then like, do some learning from it. Well, I think, the talk doesn't say that like you should do memory traces. It just says that, like, in principle, you know, decreasing, like exponentially decreasing your memory, having this kind of geometric decreasing can give you more power, or like give you ability to represent the value function in with like more simple functions than memory than window side memories. So, you know, it's not a, this is not a SOTA paper, it's really a theory, kind of findings that tries to quantify the differences between these two functions. But so, yeah, no, I mean, the honest answer to your question is, like, if you really have such problem and you want to design an agent that is, you know, that has like strong capabilities, definitely use like state space models, RNNs, LSTMs, and your favorite, or, you know, your favorite model, or like the one that fits better your type of problem. But if you want to, I don't know, have a simple representation, something that you can actually understand, you know, that can be fit into like some other linear learning model or something, like to do some theory, maybe that's interesting. So like the POMDP literature, like the RL theory literature on POMDP is only almost essentially uses this frame stacking strategy, the window of size M, right? We have results in the theory on like what happens when you have like finite windows, but we didn't have really results on what happens if you try to represent this memory in like another compressed way, and what with what kind of representations can you actually say something about it. So yeah. Now it's bright. Thank you.